Okay, this is part two. We're actually going to now solve logarithmic equations. We can solve logarithmic equations by expressing these logarithms in an exponential form and then solving the resulting exponential equation. And we actually did the opposite in yesterday's lesson of solving exponential equations. What we can do first is we can use the log laws to simplify the logarithms, and then at the end check for any inadmissible solutions. Since we know the argument, so the input to a logarithm, must be positive, and as well the base must be positive. So if we end up with any values that create a negative base or a negative argument or input, we know those answers are inadmissible because they're not in the domain of the logarithm. So a couple strategies. We want to simplify first all radicals into exponential form, and then use the various laws to simplify the equation, finally canceling logarithms on both sides of the equation by using the exponential form. Should solve most of these logarithmic equations. So let's do first solving a simple logarithmic equation, and then we'll do a more complicated one, and then there'll be two for you to attempt on your own and check solutions for. So our first one is the log of x base 4 equal to 5 times the log of 4 base 4. So our goal is to isolate for x. So we want all of our logs with x on them on one side and all of our logs without the variable x on the other side. And we actually have that from the initial setup here. We have our log with x on one side and our log with numbers on the other side. So what we can do now is we can start to apply some log laws, and actually we have one right off the bat here. This is one of the common properties of logarithms. If we have a log of a power that has the same base as our logarithm, we can simply just equate that as the exponent, because the question is 4 to the exponent what equals 4? The answer is 1. So this is actually just equal to 5 times 1. On our left side, we still have the log of x base 4. So 5 times 1 is 5, and we have the log of x base 4. And now we can turn this into an exponential because we know the log of x base 4 asks us to what exponent do we have to raise 4 to get x. Well, that exponent is the answer 5. So that means that 4 to the exponent 5 is x if we rewrite it as a power. And what is 4 to the exponent 5? Well, that's 4 times 4, well, 5 fours, all multiplied, which is 1024. And that's what x is. So what do? We put our logs with x's on one side, logs with numbers on the other side, simplified our logs with numbers, rewrote it as a power, and evaluated. So let's try that same strategy with b. We actually have all of our x terms on one side and all of our numerical terms on the other side. So let's look to use some log laws or common log properties to simplify. First, we have the log of 1. This is the common logarithm, log base 10. So this property is actually asking us what exponent do we have to raise 10 to get 1. And that exponent is, of course, 0. So this log of 1 with any base, not just 10, is 0 because any base to the exponent 0 is 1. We can't evaluate directly here our 3 log 2, so we'll leave that one for now. But what can we do here with our radicals? Well, so let's simplify all radicals into their exponential form first. So I'm going to keep that first log of x to the exponent 1/3, and I'm going to rewrite this one as an exponent instead of a radical. What would that be? Well, log of x, and this is the square root, so the exponent would be 1/2. According to our log laws, when we're adding two logs of the same base, both of the common logarithm, we can multiply the arguments or multiply the inputs. So we would get the log of x to the exponent 1/3 times x to the exponent 1/2. I'm going to write that in brackets so you can see that's the entire argument of that log. And on the right side, we have -3 log 2. So what happens now when we're multiplying powers with the same base, x? We add the exponents. 1/3 plus 1/2. If we rewrite these fractions with a common denominator, that'd be 2/6 plus 3/6, which would make 5/6. So this would be the log of x to the exponent 5/6 equals -3 log 2. Our goal is to isolate for x, so let's move that exponent to the front by using the power law of logs. 5/6 log of x equals -3 log 2. Now our goal is to isolate for x, so we're trying to move everything off of x. So we're actually going to divide both sides by 5/6, and that would give us -18/5 log 2, which again, this whole thing is just a number because there's no variable in here. Log of 2 base 10 can be evaluated in your calculator and multiplied by -18 and divided by 5. So we just have a number here on the right side, and on the left side we have log of x. How can we isolate for x? Well, we can use some exponents to isolate for x, and we can actually raise both sides to the same base of the logarithm. Our logarithm is base 10, so let's actually take both sides and rewrite them as powers with a base of 10. So we got 10 to the exponent of log x and 10 to the exponent -18/5 log 2. Why would we do that? Well, now we have one of the common properties of logarithms. If we have a power with an exponent that's a log that has the same base as our power, so 10 and 10, we can rewrite this simply as the argument x. So this in turn undoes log base 10 and leaves us with just x. And on our right side here, we have 10 to the exponent -18/5 log 2. We can punch this whole thing in our calculator and come up with a answer, or we can rewrite this term in front of the log as the exponent, and then we would have a power with a logarithm exponent that has the same base. So we could rewrite that as the argument to the exponent -18/5. And that might be easier to punch into your calculator. Otherwise, you can just punch this whole thing into your calculator. And either way, you'll come up with an approximate solution of 0.08. And we can check this for validity by plugging it into both of our logs with x's. If we put 0.08 in here, we have a positive argument. It's not negative, so that's okay. And if we put it in here, we still have a positive argument after we've square rooted. We won't get a negative number. So in terms of validity, that value is okay. We didn't actually check the value for the first answer, but if we do plug that in here for x, we would just simply have 1024 for x, and that's a positive, so we're not negative, so we're inside the domain, so we're okay. So both of these answers are actually valid. Okay, there's 2 practice questions that you can try and then check your solutions on the Moodle. That's it for part 2 of solving logarithmic equations.